All right. Today is kind of a one-stop quick lesson into transformations of functions or function transformations. And we're going to be able to analyze and write them in various formats. If you missed class, I highly recommend participating in this graph investigation portion of class, where for each function, describe how it has changed from the original. So you graph this in your original here. Let me show you. F of x equals x to the third. And then in the next line, you would graph this next function, x to the third plus 2. So I'm just going to kind of copy and paste this, and then plus 2. And what we're looking for is how did it change? How did we change from red to blue? It looks like my graph shifted upwards 2 spots, right? 1, 2. So you're going to kind of just run through and modify this equation for all these different variations to start exploring, hey, as we throw different things in front of our function or around our function, what happens to the shape as it moves around? Because we're going to make some connections between that structure of the expression and the change that's made. So go ahead and pause your screen and try that out if you weren't in class. And then when you've unpaused it, try it out for this different variation too. Notice here, we're writing a new function g based on that original function and we're changing it. So if I go back to this, okay, I'd delete that, I'd go g of x equals f of x plus 2. Or maybe I'm trying the one where it's minus 2 inside. Or maybe I'm trying the one where it's 2 times x inside. And just start getting a good idea of how this structure is going to impact the various changes to our function. Once that's done, we can kind of summarize everything that happens in notes here. So if we, after you've explored it, we're checking this out and we're summarizing in class on our note sheet the different function transformations. There's two ways that we're going to describe each transformation. The first one is going to be using a specified function. In this example, we're working with that x to the third, the thing we worked with before. So if we wanted to shift x to the third upwards, we would write a new function where x to the third gets this d added to the end of it. And if that d is located at the end, it's going to shift it up for a positive or down for a negative. Okay. The next shift we saw was that if we type in f of x equals x plus c inside our parentheses here and then raise all of that to the third power, that's a left shift and a right shift. And notice how left is positive and right is negative. That's kind of counterintuitive to what we expect. So make sure you just keep your eye out there that our horizontal shifts are a little funky. Okay. We also kind of explored that if we threw an a out in front, we'd get a stretch. So if I went f of x equals a times x to the third, we'll get a stretch in our graph. And notice how we have a few different qualifiers here as well. If a is greater than 1, we're going to stretch it. If it's less than 1, we're going to compress it. And if that a becomes negative, it's going to reflect over that x-axis. Let me just quickly show you what I'm talking about there. So let's kind of go back to that original format, f of x. If we say do 2x to the third, notice how my graph kind of stretched vertically a little more. If I do, let's say 0.5, now my graph's kind of compressed a little bit vertically. And if I do a negative, then it just completely flips over that x-axis. So the horizontal stretch is another way we can do that. This one's a little difficult to see and differentiate between our vertical stretch, but the same types of stuff will happen just from a horizontal perspective. And that b is going to be inside our parentheses. Notice how for our horizontals, oops, make that green. Our horizontals here, those happen inside our parentheses, whereas our verticals will happen outside of our parentheses because our horizontal is being grouped in with x. Our vertical is more so impacting our output, so it's taken into account after we've worked with x. Now, the same structure can be utilized if we're writing a new function, g of x, based on an original function. So if we want to get a vertical shift, we'll just write our new function. We'll say, hey, it's equal to whatever f of x is plus d. Same thing with the horizontal. Our g of x is equal to whatever f of x is, but now we're going to plus c inside our parentheses. So we can modify this graph, and let's go to Desmos and check it out. If I write, okay, g of x equals f of x, I can modify this graph just by making a transformation of the original, adding 3 there, on the inside adding 3, and it moves it in various directions. Again, note that the horizontal takes place inside of our parentheses, and there's that kind of opposite expectation with our left and our right directions. Okay, then lastly, our vertical stretch and horizontal stretch. So in this case, all we're going to do is multiply by a or b. And for our vertical, a goes on the outside, so a times f of x. And for our horizontal, b goes on the inside, so f of b times x. Now, lastly, we can put this all together in one mega equation if we wanted to. So this is on the bottom right corner. If we're writing some new function, g of x, okay, we can write a big modified version of this f of x, where we get, okay, our a is multiplied on the outside of f, our b is multiplied on the inside with our x there. Then we would add our c, and we would add our d, and we can get a combination of things where there would be a vertical stretch, a horizontal stretch, a horizontal shift, and a vertical shift all in one. Let's look at that, a quick example of that. If I take this x to the third and say, okay, let's say I vertically stretch it by 2, and I want to horizontally compress it by 2, and then I want to shift it left 4, so I'm going to add 4. And let's say I want to shift it down 3, so I'm going to subtract 3. All of this stuff changed our function over time. So let's start practicing these applications. And while you're doing this, absolutely have your Desmos pulled up alongside of it so you can kind of visualize what's happening. So examples 1 through 4, describe the type and size of the transformation for the base function f of x equals absolute value of x. So first thing I'm going to do is I'm going to get rid of my 2 functions in here, and I'm going to change this base function. And we're saying, hey, the absolute value of x. This is something we're going to work with in the future. Notice it's a very funky shape, but we get this base function here. Now, if I graph f of x equals the absolute value of x minus 4, you'll notice that my graph has shifted down 4 spots, right? 1, 2, 3, 4. It's gone from 0 to 4. So our answer there for our kind of describing the shift is a downward shift of 4. And we should have been able to predict that based on the location, that negative 4 at the end. Kind of matches how we place our different vertical shifts, right? It shows up at the end of my function. It's a vertical shift. It's negative, so it's downward. Okay. Example 2, it's inside with my x, and it's a value that's greater than 1 if we look at our kind of horizontal stretch compression rules. So this means it's going to kind of horizontally compress my graph by 3. Horizontal compression of 3. And if we graph this and we look at it, okay, we have our original one. I'm going to modify this blue one here, and we throw 3 on the inside. Notice how this blue got pinched inwards. It got compressed from the original graph that's red. Okay, definitely start trying this on your own for 3 and 4. We should know by the location of this that we are going to shift right, or it's a right shift of 2. And for example 4, we are going to reflect over the x-axis. All right, so if we check this out, example 3, let's try it and see. I go back, I type in my equation, -2. Looks like, yep, our blue graph shifted to the right twice. And if I go to example 4, I throw that negative sign out in front, boom, we do get that reflection over the y-axis there. Now, we can take this in the other direction. If we are starting with this base function, we want to write a new function based on a description, shifting up 3, we can do that, all right? I will have my f of x, it equals the absolute value of x, and since we are shifting up 3, we're going to use that d location, we're going to add 3 to the end. Now, if we want to, in example 6, actually, let's just confirm that that works. If I go back here, go into Desmos, retype this, getting rid of my negative and adding 3, it looks like indeed we shifted up 3 spots there. So compressing, we're going to have 2 things come into account. We want to compress vertically by 0.5, so outside of my absolute value sign, I'm going to want to multiply by 0.5. And I'm going to want to shift right 2, so that's going to subtract by 2 there. And let's check, let's see if we did that correctly. So we go in, we modify this, 0.5 times x minus 2. I can easily see that I have shifted to the right 2 spots. It's a little difficult to see if I vertically compressed it by 1/2, but you can see if I get rid of that shift there, it is vertically smushed down a little bit. It's not as high up. So I'm going to say that looks like we accurately did that. All right, we are basically going to rinse and repeat, but for this kind of new function notation where we're writing a function g that is transformed from f. Let's try this out. In this case, we're just describing the shift. If I kind of rephrase what's happening in Desmos here and just say, okay, g of x is now equal to some transformation of f of x, we should be able to work through this. And based on the structure of this one, this looks like it's going to shift left 3 spots, right? Because I'm inside my parentheses. It's a positive, which is kind of opposite of what we expect. And if I test this out, it looks like, boom, our blue graph moved to the left 3 different spots. All right, if we multiply on the outside, we should get a vertical stretch of 2. Let's test that out. Vertical stretch of 2 here. Let's see, I delete my old stuff. And if we multiply it by 2 in front, nice, it does stretch up vertically. Tough to see if that's of 2, but we should be good. This is coming on at the end in example 9, so it looks like it's going to be a downward. We're going down 11 spots. I can test that out. G of x minus 11. This one I might need to zoom out or scroll down a little bit. It looks like my y-intercept moved from 0 to negative 11, so we did indeed shift down. We home back in. And this last one has a couple things going on. We have this 1/2 in the middle for horizontal. So that's going to be a horizontal stretch because horizontals kind of work the opposite of 1/2. And we have a upshift of 3 going on. So looking at that, f of x, let's try that out and modify that 1/2, and then we are adding 3 at the end. It does look like horizontally we've spread out more, so I'd agree that's a horizontal stretch there. And then we've added 3, we've shifted up 3 on our graph, so we should be good. And last but not least, we can go in the other direction as well with this notation. If we're going to try to shift it to the right 6 spots, we can write g of x equals f of x. In this case, if we're going right, we'd want to subtract 6 because the horizontal kind of works the opposite. And if we want to try out example 12, we got two things going on here, the horizontal stretch by 2 and the shift down of 4. So I know I'm going to have something going on in my parentheses because I'm dealing with horizontals. So that horizontal stretch of 2. And this one's really tricky because we want to actually, well, I'm going to go back and apply this question. So make sure you update this with me. Really, if we're using that 2 factor, it is going to be a compression. Compress horizontally by 2. So that's going to go in here. And then we're going to shift down by 4. That's going to go on the outside, minus 4 on the outside. So f of 2x minus 4. And let's check that out. Okay, and I'm going to check out this stretch or this compress before I go. It looks like the blue is compressed in a little bit, so we should be good. And then if we subtract 4, that graph shifts down 4 spots. So that matches up as well.